And we are back. So we can actually analyze sound examples in Mathematica, and this is a great kind of example of how you can perform a Fourier analysis. So hopefully you could hear this. Let me just be quiet. So that's a clap sound. So you could hear violin sounds as well. You could hear combinations of notes. And we could kind of start to analyze this data. So we have a sound, we could extract or look at the audio data. We could look at the sampling rate, which is going to be critically important. So this is our F sub S for this data set. And we can start to plot and look at what are the voltages or what are the values, the magnitude essentially of this sound data. So we can look at these in terms of spectrograms as well. You can see again, we're plotting to our, basically we should be plotting to twice our sampling, or our Nyquist frequency. So again, once you should be half this value, but anyways, so we can plot essentially the spectrogram and kind of see some of the different frequencies that are present in our signal. So we can set, and actually we could plot this ourselves. So I can go ahead and I could plot my F sub S. I could look at the length of my pedogram, and then we can actually start to plot this. This may take quite a while because, and actually we will abort this. But we could look at the result here. So we could just kind of look at this. This is not plotted in terms of our frequency spectrum. So again, when you're plotting on the x-axis, you want to look at your F sub S divided by the length, divided by n, the length of your data set. Why? Because this is going to give me my delta F, my fundamental frequency. But what we can clearly see here is that when I'm looking at different notes, G, G, G on different instruments, I see the magnitudes may change here, but I see the same frequencies line up. There's no shifting in the frequencies here. So if I zoom in on two examples, the violin and the flute, here I see I'm getting the same frequency results. But once I shift notes, G to A sharp on the two different instruments, or even on the same instrument, I see the shift occurring here, which should make sense. And actually, let's go ahead and shift here. Violin. Let's do A sharp on violin. Let's look at this. There's quite a bit of data on this one. So let's be patient as we, again, actually this is why it's not working, or not working, but I'm going to abort this evaluation, and I just want to look at because what I'm really just interested in is this. So let's go ahead, forget about transposing it for a moment, instead just look at the data like so. And again, you can see the shift in the data set. So the frequencies shift as we expect, because again, we're doing a Fourier analysis. We're trying to figure out what are the frequencies in our signal, and there we go. So now that is basically how you could do Fourier analysis on sound. You could also do Fourier analysis on images as well. So let's take a look here. I could do image periodogram. So this is going to plot my power spectrum for different images. So I could put this image here, and these bright dots are going to indicate effectively structure or periodic distances or kind of these characteristic distances in my signal. So if I see these bright dots, that indicates a well-ordered structure. If I see kind of this amorphous amorphous or kind of diffuse background, that's telling me that there's not order in my system. So for example, if I look at this crystal image, I believe this is maybe graphene. There's clearly, it looks to be six-fold symmetry in the system. So if I do my image periodogram, I see these bright dots that are kind of almost hexagonally ordered here. So I could almost see kind of a six-fold symmetry. If I blur the system and I do this image periodogram, I see nothing. These lines here are coming from essentially the edges of my system. And you could do it, if I blur it a little bit less, I could see, again, still very, very diffuse, but I could try to see a little bit of, if I just do 1, for example, then I start to see those. But if I do 5, so you could kind of lose effectively some of the distances. So anyways, that's kind of what we're seeing here. But if I sharpen it by 1,000, I could really start to see, or let's just do it by 10. I could see, you see how here compared to, let's just do image periodogram of crystal. I see more distinct distances because, again, I'm increasing the contrast or the sharpness in this image. So I can do the same thing with this image here. So clearly I see this six-fold symmetry in my system. But I could actually use a Fourier filter to kind of clean up the noise. So this is actually a nice little technique to utilize in your system. And then I could do my image periodogram. And I see, look at all these dots, because I see, and I'm looking at here, all of the structure. So I'm seeing these bright dots because I have a periodic structure in my system. And you can see kind of these almost like, they look like electron clouds. But these indicate kind of the six-fold symmetry here in the system. So the arrangement or the orientation kind of tells us that six-fold symmetry. So I could do blur and sharpen, and I could kind of just, again, try to increase essentially this contrast. But I could see, again, very, very, very nice. Again, make it black and white so I could clearly see the distance of my material. If I look at a material here that has tons of defects, so I clearly see, look at, there's some, vacancies here, there's some edge dislocations here, there's grain boundaries all along this boundary. If I look at this, even if I sharpen, I see this diffuse ring system. So it's actually pretty cool. So actually, if I even just do defects here, I see these diffuse rings. That indicates, again, I have some structure, but it's a little bit, there's defects in my system. There is some long-range order, there is some characteristic distances, because again, this is showing us this inverse space, so reciprocal space. So there are some characteristic distances between my particles, but I don't have those bright dots that indicate that orientation or that fold symmetry here. So you could filter this as well, but it doesn't do as nice of a job as the previous system. But still, does pretty well, especially when you can zoom in here. So this versus just defects in general. Let's try to zoom out. So it does an okay job, but again, not as nice as the other system. You may have to play around essentially with your with the parameters here. So 0.1, maybe 0.2, but these take a while to run. So yeah, it improves a little bit. You can get a little bit. Let's do 0.5. Let's see if we get any marked increase in filtering ability, but not really. But you can kind of start to see some dots here. So actually, it's a nice little filtering aspect. So you start to remove some of the noise here effectively. It's almost kind of like putting a Gaussian filter. And then finally, Laplace transforms. Again, you could take a function and then you can take it in time space and you can transform it in frequency space, or your basically Laplace frequency S. So hopefully you've seen this table before. And then in our problem sets, we're going to do fun examples related to passive microrheology, where we take the mean square displacements, we fit it, we do a Laplace transform, and then we can find our G prime, G double prime. All right, thanks. And that is pretty much it. So next time we're going to get into ODEs and solving ODEs. So I'll see you all next time. Thanks. Bye.